Okay, anybody got any questions before we start? I will address some questions that were brought up by one of your peers. That is the practice exams are like exams 1 through 4. They're regular hour exams. They're not a final exam, but the structure and content will be similar. So imagine, if you will, kind of picking some out of each of those, and that's what it would be like in terms of like what kind of questions would be a good question to ask for the spectroscopy section, or what would be a good multiple, or well, I guess I don't have multiple choice, but what would be a good short answer question for the stuff on statistics. So if you get through those, you should be in pretty good shape. I will gladly go over those in office hours with you if you want to go over those. As far as an equation sheet goes, I will be making that up hopefully today. I did get COVID shot number 2 yesterday, and so I've got a pretty bad case of man flu. I mean, you might as well just like break out those dancing pallbearers and like cover over your F key and maybe get out your Zippo, because I think a Viking is going to die here. But hopefully I will be okay enough to write that. Again, with the equation sheet, any equation you think you might need, I will give it to you. So if you find any equation in the book, or you're like, yeah, is this going to be on there? Yeah, I'll put that onto that equation sheet for you. As far as homework goes, I will have to check and see which is the last one that I'm going to grade. So I've got some of the extra ones that you can use to practice. As far as practice goes, I am also going to reset the deadline on all of those. So if you need to go back and like give another crack at one of those homeworks, or use them as something to practice and study with, you'll have that opportunity as well. If you want to do the quiz, my take is still you got to come to office hours, and we'll do that privately, just so that there's not copies of those quizzes floating around. But I will be glad to go over your quizzes in office hours. Let me see. Okay, you guys have any questions about that? Here, okay. Maybe, possibly. All right, if you think of questions you've got later on, let me know. You know how to get a hold of me. All right, so we left off talking about detectors. And so detectors are going to be the eyes of our spectroscopic instrumentation. They're what's going to transduce a photon into some other measurable signal, usually as some sort of electron. And we left off talking about the photomultiplier tube, which is really just a fancy photo tube where you've got a photon coming in, it hits this photosensitive cathode, it converts that photon into an electron. The electron zips off towards the dynode. This dynode multiplies one electron into many electrons. That then cascades through 9 of these guys, and this is the circuit diagram for that, until it finally drains out at the regular old anode, where you get 10 to the 7th electrons for each photon that comes in. And so you're really boosting your signal relative to a plain old ordinary photodiode. So this means that your photomultiplier tube is more sensitive. It can detect fewer photons. On the other hand, you would not, so like if you were doing a fluorescence experiment where you're looking at maybe 1 out of 10,000 photons that you throw into it comes back at you, then yeah, you'd want this, where it's a low light application. If you're doing something like UV vis, where you've got a whole bunch of photons coming through, and you're looking at a drop of those photons, then a regular old photo tube is what you want, because you don't need that kind of sensitivity. You got plenty of photons to work with. So regular old photo tube, good for high light applications. Photo multiplier tube, good for low light applications. Okay. We also have photodiodes, and they're going to work like an LED, but in reverse. So an incoming photon is going to generate a current by moving an electron or a hole from the valence band to a conduction band. And we said earlier that we got 2 types. We've got an N type, where electrons are the charge carriers, which are negative, or P type, So the holes are the charge carriers, and those are positive. They're easy to make. Photodiodes are easy to make, and they're really, really, really cheap. So a lot of the things that are like little night lights, they're going to have like a little photodiode in there. They might have a photoresistor instead, which is going to change its resistivity based on incoming photons. The advantage of these guys is they're really, really easy to make. And they've got a sensitivity that's somewhere in between a phototube and a photomultiplier tube. So a good photodiode is going to be competitive with a photomultiplier tube, and a cheap one is going to be competitive with a regular old phototube. Why don't you see these more often? A lot of it just has to do with inertia. Like I've got a machine and it's using this and it's got this design, and it has been the same design since the 1960s. And so, you know, people want things that are backwards compatible with what they've done, even though something newer might come out. So this photodiode is going to work on this idea of a pn-Junction again. So you've got a potential that is applied, you've got a positive and a negative, and you're looking at the flow of electrons that are able to move. So electrons are able to move this way into the N region. It's going to displace electrons from one spot. It's going to bump into this guy, which bumps into this guy. On the other side, you're pulling electrons away, and you've got whole migration towards the middle. This means that electrons can flow when it is in a positive bias. If you have a reverse bias diode, right? So if you take this guy and you make this guy the minus and you make this guy the plus, well, now you're going to end up with a depletion zone in here, right? And as that depletion zone gets bigger and bigger and bigger and bigger, it will eventually reach a breakdown voltage when current will start to flow. And if you have a reverse bias diode, you can make what's called an avalanche photodiode. And so it is right at the breaking point. And what happens is that photon comes in, it basically breaks. It's like throwing a keg of dynamite into a dam, and that dam has been holding back a lot of current. And as soon as you get that extra photon in there, that dam breaks and current's allowed to flow. So avalanche photodiode, those are like one of the most, if not the most, sensitive detectors that we got out there. Increasingly, you will see charge-coupled devices. Most modern instruments, spectrograph, spectroscopes, spectrometers, are going to use a charge-coupled device. And they were developed during the Polaris missile program. So the Polaris missile program, they wanted to have a guidance system. So this is in the days before GPS, 1960s, I think. And what this thing would do is they would launch this missile, and it would go up, and it would basically take a picture of the sky, and then it would use the stars to take a picture with a charge-coupled device. It would use the stars to figure out where it was, and then figure out where it needed to go over in Russia or wherever they were sending this missile. The somewhat comical problem with that was that we have cosmic rays that are constantly shooting through the universe. So there's these high energy photons that are just there. And occasionally what would happen is the missile would go up, it would take a picture, cosmic ray would come in, hit the detector, and all of a sudden the detector would think, oh, there's this really bright star here, and then just like change its orientation and just crash. And they figured out how to adjust that with like ways to reduce that kind of random noise in there. But yeah, they lost a couple of missiles because it was like, oh, look, I'm going up. I'm confused. Where am I? They were developed by NASA for satellite imaging and planetary imaging. So you can detect a lit cigarette on the rings of Saturn from Earth using a charge-coupled device. Bonner Denton was like, hey, you're detecting photons. We can do this for chemistry. He was a really interesting guy. So he was out at University of Arizona. And he's got like some sort of, he's a big car guy. He's got like some land speed record, or had one for like some class of car. And so he's doing all kinds of cool stuff. So he was like, you know, why don't we use this as a detector system for a spectrometer? And they're also what's used in a high-end digital cameras. So if you get like one of the, you know, couple $100 to $1,000, not like a cheap phone camera or something, but like the high-end digital cameras, like Kodak, I think, still makes a couple, or the high-end Nikons or Canons, they're going to use a charge-coupled device. That's in competition with what's called CMOS imagers, so like a webcam or your phone. CMOS stands for composite metal oxide. And those CMOS sensors, they are on your phone because you can make them in the same production process as the rest of the integrated circuits on your chip. So you can make these sensing areas on your same lithographic process. Whereas if you got to do a charge coupled device, that's a whole separate process. All right. So those are the components. Right? We've got some sort of light source. We have some way to do wavelength analysis or selection. We have a sample that interacts between the matter and the light. So if you're doing emission, then our source and our sample might be the same thing. And then you've got some sort of detector that's going to detect those photons. The way you can arrange these parts are going to give you different flavors of instrumentation, which are going to have different pros and cons. Okay? So the four that we're going to talk about are the single beam instrument. This is like a Spec 20. This is a very simple spectrometer. This would be like if you had that little spectroscope that you look through, you would be acting like a single beam because there's only one beam. You've got a double beam instrument. That's like the one we used for the UV vis in lab, so like our carry spectrometer. You've got a multi-channel instrument. The detector in the HPLC is actually a multi-channel instrument. The detector in, can't remember if the detector in the ICP is a multi-channel or not. I would have to look into that. And then Fourier transform. So a Fourier transform or an interferometer is going to be what you saw for any time that you did FTIR. So just about any infrared analysis that you're going to do is going to use a Fourier transform. So let's look at our block diagram for a single beam instrument. So got a source. Okay. We have some photons that are going into a filter or a monochromator. We have a shutter that will block photons coming out. We've got a reference cell, a photodetector, probably some sort of amplifier, and then a readout. So what you do is you physically put in your reference, right? You write down how many photons get through. You take out your sample cell, replace it with the reference cell. You measure it over here and figure out how many photons are getting through when your sample is in there. And then you can change the wavelength and build up the spectrum one position at a time. So obviously, there are some advantages to this. This is the simplest type of spectrometer you can build, right? It's just all these things are in a line and you just got them and you just replace your reference with your sample. What do you think some disadvantages to this are? Well, if I've got some variability or noise coming from my source, that's going to show up in my readout. There's no way to correct for wandering potentials or changes in your photon output. So when you go and you put your sample cell in, right, it may look like light is absorbing, but really your light bulb just got dimmer. Right? And there's no way to really correct for that unless you take lots and lots of measurements. If you have to do this, you got to put in your reference cell, right? Blank it out. No, I've not uploaded that. I will give you guys one standard size note card, front and back, or the equivalent volume or area in space. So I will figure out what that area is. So you get one standard 3x5 note card, front and back, that you can put whatever you want on that. I will want you to include in your exam a picture of that front and back note card as part of your submission then. So I will give you the formula sheet as soon as I make up the formula sheet, but I will put any formula you want on that formula sheet. All right, so on your note card, don't go put in any single formula because I will give you that. Now I won't give you like a dimensional analysis, like how do I go from mass to moles? Or how do I use density? And so that's not really a formula, that's a process. But any sort of formula or equation you think you might need. Lab notebooks, let's make them due next week. So Monday's lab notebook would be due a week from yesterday. Wednesdays will be due a week from Wednesday. So cleanup went pretty well on Monday. Hopefully we'll be able to get out in less than an hour on Wednesday and Thursday as well. All right, so we got two different problems. One is, what if I got variability in my source? And the other is, yeah, it's kind of a pain to take this guy and put in the reference cell, put in the sample cell, put in the reference cell, put in the sample cell. It's kind of a pain in the ass to do that. Because anytime you take that thing out and put it back in, you're going to have positioning error. So one of the things that you can do is switch from a single beam instrument to a double beam instrument. And a double beam instrument is called a double beam instrument because it's got, count them, two beams of light. So you got your source and you got your monochromator. This is the same here, but then you're going to go to a beam splitter. Okay? And one of the beam paths is going to go through a reference cell, right? And we'll measure the photons that get through to this reference cell. And then the other beam path is going to hit a mirror, go through our sample cell, and it's going to hit another photodetector. And we're going to use what's called a difference amplifier to basically do that conversion to transmittance for us. And then we'll get a readout. Right? So now if I've got variability in my source, right, it's going to give you the same fluctuation on both beam paths. I don't have to take my reference cell out anymore. Right? I can leave that in place, and now I'm only moving out my sample cells. Right? So this is a step up. I've accounted for one source of noise. Problem is, now I've got two photodetectors. What if the response of photodetector number 1 is different than the response of photodetector number 2? Right, so photodetector number 2 starts to go out, right, and starts to not respond. It may look like when I get to this difference amplifier that fewer photons are getting through. My absorbance is higher than I think it is, and my concentration is higher than I think it is. So I've introduced another potential source of error by having a second photodetector in here. Do you think there is a way we can get rid of, so we can get rid of the two photodetectors, but still keep this reference path and the sample path? And the answer is yes. Right? You will very rarely see this anymore, right? There are still some instruments that are made that have this kind of configuration to them, but very few. Most of them are going to follow this, which is the same configuration as in our carry UV viz that we had for a lab. All right, so let's go through this. All right, so we've got our source, we've got our filter or monochromator. That part is exactly the same. But once we've picked off our wavelength of light, we still have two beam paths going through here. But rather than having a beam splitter, which sends them two ways, we actually have a motor hooked up to what's called a chopper. And it's called a chopper because it's chopping up the light, where you've got holes, right? So you got a transparent part here, and then you got a mirrored part here. It's also called a chopper because that thing is spinning really fast, and if you stuck your finger in there, then that's exactly what would happen to your finger. So this chopper, it's spinning, it's spinning. And as it is spinning, if it hits the transparent part, light will go through to the sample cell path. If it hits the mirror part, it's going to go up towards the reference cell. So we still have, and because this guy is spinning really, really, really fast, right, we're still going to send roughly the same beam each way, right? So if I've got fluctuations in my light source, they're usually pretty slow, and the rate at which this thing is spinning is faster than any changes over here. So we're sending the same light path towards our reference and through our sample. So our sample path goes through our sample cell. It's a mirror, and then goes to either a grid mirror or it goes to another chopper. And then it bounces off there. And so half of the light in this grid one, it's really just like, it literally looks like a grid, where you've got parts that are going to be reflective and parts that are going to be holes. And so some light is going through this way and getting wasted. Some light is going through this way, hits a mirrored part and goes to this detector. And so we've got a measurement at our photodetector. And then on the other path, photons come through here, they hit the mirrored part of the chopper, go through our reference cell, goes to the grid mirror. Some of it gets bounced up this way. Some of it gets passed through. And so what you see at the photodetector is an alternating signal that's coming from both your reference path and then your sample path. And it's really switching back and forth between the two really, really, really fast. Okay? And we can easily keep up with like what those fluctuations are, send that to an amplifier, and then we have what's called a null detector to see if they're the same or if they're different. Okay? So this is a by far more common version that you will see. Sometimes they will replace this guy and put another one in here. They'll do two grids. The Carry UV-Vis downstairs has a chopper here and a chopper over here. The optical wedge just doesn't show up in that one. The disadvantage of that is you've got this in here, in this chopper, right? Don't stick your finger in there is the obvious thing, but if you're an engineer, anytime you have a moving part, that is one more thing that can go wrong or go bad on you, right? So if every time you're running a UV-Vis like this, right, that chopper is spinning, and it's spinning fast, and it's spinning the entire time you're doing it. And eventually that motor is going to wear out, right? Or it'll have to be replaced, or you'll lose communication to it. And that's actually one of the most common modes of failure in those instruments is, yeah, my chopper's not working anymore. Right. And once this thing starts to go, that's pretty much it for that. You know, like you can't go in there and get a pacemaker and replace it. So this chopper here is the part that's going to go on it because it's a moving part. Right. Moving parts. If you want to avoid moving parts as much as you can, one way to do that is to use what's called a dispersive instrument, or a multi-wavelength instrument, or a polychrometer. And so this is a schematic for one of these. So you've got your source, you send all of your photons of all wavelengths through your sample. It gets focused from a mirror through a slit, and then you've got a focusing grating. So your grating is going to do two parts. It's going to do two things. It's going to project onto a focal planar array. So it's going to focus your photons down to this photodiode array, and it's going to break your light up into its component wavelength. So you have, red over here, blue over here, and each diode. So there's going to be like 100, 400 diodes, right? Hundreds of diodes on here that are then going to pick up each individual wavelength, right? And so the easy way to think about it is I've got, 400 diodes. Here's diode number 1, and we're going to call that 400 nanometers. And over here is diode number 400. We'll call that 800 nanometers. And each diode in between measures 1 nanometer's worth of light. Disadvantages to this method, there are a couple. This part here, this focusing grating, can be expensive because you not only have to have a grating, it's got to be on a curved surface. You are also putting through a lot of light through your sample. So for something that is a delicate molecule, maybe you don't want to throw through, blue and red and green and violet light, right? You just want to do one wavelength at a time. The advantage of this, another advantage of this, is that this is really, really fast, right? You're going to get your entire spectrum in less than a second. And so when we did the one downstairs on the Carry, where we had that double beam instrument, we had to wait, and you turned that grating, right? 400, 401, 402, 403, 404. And as you turn that grating, you would slowly pick through each individual wavelength of light and pass through one wavelength of light at a time. Right? So you have to wait for this thing to physically transition. Right? On the other hand, here, right, the only moving part is this shutter, right? Each wavelength of light is getting measured at the same time. It's a lot faster. You're going to get a little bit more sensitivity because of what's called the throughput advantage, because you're putting through all of those photons at the same time, and you're not throwing in an extra shutter to block out some of the light. Some of the instruments don't use a photodiode array, like really the separations people are the only ones doing photodiode array anymore. You're going to have a CCD. A lot of instruments now are not even going to have a CCD. Some of them might even have a CMOS because CMOS is getting that much better. So that you've got a completely integrated package and you've got no moving parts. These guys are fast. So we've got an instrument that will do a full spectrum acquisition in about 35 microseconds. Right? So that's fast, right? So it's a really, really fast way to get a full spectrum. So there are definite advantages, and these guys can be really small, this big, right? You know, compared to that Carrier, which was like that big. Right? It was a beast. And the reason why part of the reason why that Carrier was such a beast was that, yeah, you did have those moving parts in there, and so you want it to be a nice, stable platform. So there's a big, heavy ass metal plate, right? It's like Bender's ass, right? It's 90% vanadium. It's big and it's heavy so that it doesn't vibrate and wobble around, right? Because you've got those moving parts in there. And if you got something that's jiggling and is moving, well then you could end up with an error or light going in different directions. Here, these guys are smaller. They don't need that plate. Once you get everything in position and it's locked down and glued into place, right? You've got a shutter, right? Open and closed, right? Not much to worry about there in terms of positioning error. And then you've got the cell that goes in and out. You can't avoid that. In the case of something like an atomic absorption experiment or an atomic emission experiment, you can have the sample be part of your light source, or it could be a hollow cathode lamp. So hollow cathode lamp is going to be a light source for an atomic absorption experiment. So this hollow cathode lamp is going to give you emission lines. Right? We've got the same two-path system that we saw with a chopper. One path goes through a reference beam, and it's going to give you these lines, these emission lines. The other beam path is going to send this emission line through a cold gas, and those cold gases are going to absorb the corresponding line. So that's atomic absorption that's happening. So you're going to put these individual lines through. This cold gas is going to absorb some, and you're looking at, well, if I put in, 300 photons of red and I absorb 100 photons, how much light did I lose? It's an atomic absorption process. This is in atomic absorption spectrometer. It doesn't really show the inside, but the idea is you've got this like burner flame here, and that is your cell path length. So this length here is your path length. Last up, we've got the interferometer. So our interferometer is not going to work in UV visible wavelengths, but it will work in the infrared and longer wavelengths. Nice thing about an interferometer is that it's still going to enjoy that throughput advantage that you saw with our polychrometer or with our multi-wavelength systems. The way it's going to work is you send a photon down this way. It hits a beam splitter. The beam splitter is going to send some of the photons up to a stationary mirror and then back down through that beam splitter to the detector. Some of the photons are going to go through path B to where they're going to hit a movable mirror, return, meet up again with the photons that went at A, go through our sample and hit our detector. Okay? And because A and B can have different path lengths, what you will do is you will have constructive and destructive interference of those photons that went on path A versus path B when they recombine at the detector. So when they land at the detector, you're either going to see a combination where A and B add up or where they're going to decrease. Our sample is going to absorb some of those photons, but what we will produce is what's called an interferogram. Right? So we've got, here is our basic setup. We got two different path lengths, right? You guys have seen like the double slit experiment before, where you've got, for example, two little holes, and then at the other end, you see like, oh, this is part of like how we prove light as a wave. Right? So if we got beam A and beam B, they're going to interfere with each other, both constructively or destructively. And at the output, we'll have a series of constructive and destructive bands of photons. So if I've got one wavelength coming in, right, it's going to look like this. Right? So it's got bright spots and dark spots. And that's corresponding to a photon where I've got one wavelength that's got a period to it, or a wavelength, and it's got an amplitude to it. Right? And I've got one frequency involved. Right? If I've got two wavelengths, those two wavelengths are going to interfere with each other. So here I've got wavelength nu, and here I've got a wavelength that's coming in at 4 nu. So it's like 4 times as fast. And our composite wave is going to be the sum of a wave that looks like this, and then one that had 4 times that frequency. And so you're seeing the superposition of those two waves. One's coming in at a lower amplitude, but a higher frequency. That's this little wiggle on top. And then one that's got a higher amplitude, but a lower frequency. That's this part here. If I do this a lot, I'm going to end up with what's called an interferogram. So an interferogram is, as I displace this mirror, what does the power at the detector look like? And ideally, let's see if I can draw this. All right. So an ideal interferogram is going to have this decaying exponential function to it. And if I had a single source, it's going to look like that, where I've got up and down and up and down and up and down. I got one wavelength, and it's going to be a decaying exponential. If I've got two wavelengths in there, see if I can draw this. All right, it's going to be that doubly weird shape where it's got the up and the down, and then up and down and up and down. And it's going to be like that other more complicated guy that we saw back here, but applied to a decaying exponential. If I absorb photons of a particular frequency, what I will see in my interferogram, which would ordinarily be like this, is I'm going to see a notch or a gap at certain frequencies. And that notch or gap, when I go through what's called the reverse Fourier transform, so I undo my Fourier transform, so I do a Fourier transform, I'm going to go from the time domain into the frequency domain. And so it's changing, like over here, we've got something as a function of time. And on this one, we've got something as a function of frequency. So here we've got one frequency that's corresponding to a one wave frequency. When I do my FFT and I take my interferogram and I Fourier transform it, I end up with the absorbance spectrum. Right, there's my absorbance spectrum. This guy's just power. Power at your detector. And then this delta is your displacement. Right? So how am I moving that mirror? And I can end up with a spectrum that looks like an an infrared absorbance spectrum, where I've got absorbance or percent T on my y-axis, and then my x-axis could be in something like microns. So sometimes you'll see microns or centimeters to the -1. So some sort of wavelength or frequency axis. You cannot do UV-Vis or FT-UV-Vis or FTIR because you would have to move that mirror either in such tiny increments or so fast that you would end up breaking things. FTIR is or IR is really useful because that energy that's associated with the IR region corresponds to molecular motion. And because each molecule has its own unique physical structure, right? The atoms are hooked up in a particular way, right? That's what makes one molecule different from another molecule. But because those molecules are hooked up in a particular way, they're going to have their own unique set of vibrations. Now, some vibrations are going to be similar to each other, right? So if I've got a carbon-carbon double bond, right? All carbon-carbon double bonds are going to be pretty close to each other, but they're not going to all be exactly the same, right? So this is like saying, yeah, we got a bunch of basketball players and they're all pretty tall. And over here, we've got a bunch of, I don't know, wrestlers, and they're all pretty squat and sturdy. So they're going to be similar, but they're not all going to be the same. And what we're looking at in the infrared region here is things that correspond to those molecular motions. And if you're a different molecule, you're going to move differently depending on which molecule you are. So when you're looking at these, you're able to figure out, okay, well, what is my functional group here? All right, this over here, this is sometimes called the fingerprint region. Right, because this has all of those carbon-carbon stretches in it. Right, so it's real hard to predict where any given carbon-carbon stretch is going to happen if you got some big organic molecule, but they're going to be unique. And so looking at this, right, you can match up a spectrum to a reference library. You can kind of make some guesses about what this thing is going to be. So this guy is vanillin, right? So in a chloroform solution, right? So you can see things, well, here's an OH group, right? This OH group over here, right? That's that OH group. Right? It's relatively high frequency. Looking at this, you've got high frequency, and over here you got low frequency. And when you're looking at these things, you got to make sure that you are looking at what this axis is. Because sometimes it is in centimeters to the -1, but sometimes it is in microns or micrometers. You will note that this guy's got inverted peaks because this is usually in %T. Now, why it's in %T versus in absorbance, I don't know. I'll have to look up why they would do that. My guess is it was just instrumentally simpler at some point when people were making these and nobody ever changed it. It might also be because these peaks, right, these inverted peaks here are sharper and easier to see on a non-log scale. Right, so remember that our absorbance is going to be minus the log of the transmittance, right? So if I took these guys and I made them into a log scale, then maybe those peaks would shrink a little bit and it'd be harder to see what was going on. The reason why you will see these in two different units on the top, though, this is microns, this is wavelengths, right? So this microns is like nanometers, it's just down in 10 to the -6 as opposed to 10 to the -9 meters. So it is the next order of magnitude down, or next 3 orders of magnitude down. So that's, yeah, you can do anything with IR that you did with UV-Vis for the most part. So all of the things that you can think about, like Beer's law, are still going to apply. They just might be a little bit trickier to implement. You're still going to have a molar extinction coefficient, right, that you could figure out for this peak. Right? So you could figure out an epsilon value for this guy. But oftentimes you will see this as frequency. And the reason why you will see it as frequency is because of this frequency here corresponds to the energy or the frequency in this vibration up here. And so this guy is really hiding not frequency, but energy. So when they put this in centimeters to the -1, that's really an energy axis, and you can use that to compute what the energy of a particular molecular vibration is. Some modes in IR are going to be visible, right? Some will show up, some will not. There are what we call selection rules for this. So when you are looking at a particular molecular stretch, some things will be active and some things will not be active. So for example, if I'm looking at carbon dioxide, a particular stretch that is symmetric, and so here's my oxygen, here's my other oxygen, and if I do a symmetric stretch, that's not going to show up in IR. If I'm looking at an asymmetric stretch, that will show up. So your selection rule is that you have a change in from the dipole. So you've got to have some sort of oscillating molecular dipole. And so if I look at my carbon dioxide, and if I symmetrically move this guy way out, move this guy way out, right, I have a partial positive here and a partial negative there. Right? And this is balanced out by the partial positive and partial negative here. I have no net change in my dipole if I just symmetrically stretch these guys out. If I go with an asymmetric stretch, right, now I've got a partial positive and a partial negative here. And over here, I've got a partial positive and a partial negative. And so now I've got this net dipole that's going to be slightly towards the right. And if I bounce this guy back the other way, it's going to go towards the left. Right? And so I'm going to oscillate between having this dipole go to the right and go to the left, go to the right, go to the left. And this one, it just kind of goes out and in, and I get no net change in my dipole. Here with this asymmetric stretch, whereas my symmetric stretch, right, so my asymmetric stretch is going to have this oscillating dipole. My symmetric stretch will not. So this guy is what we call IR active. And this guy over here, my symmetric stretch, is either IR inactive. Sometimes you'll see it's called IR blind. I'm not going to see it. We got no peak. Right? Because this asymmetric one, we will. Different functional groups are going to show up in different places. So for example, our OH, or aliphatic or aromatic ones are going to show up at relatively high wave numbers. Right? So this guy's going to be high wave numbers. That's a high frequency. So if you've ever done the thing where I don't even have a ruler. Where you take a ruler and you go boing on the edge of your desk, right? And then you move that a little bit closer, right? That's going to change the pitch at which that ruler, and you can buy like musical rulers that are tuned. So that's going to change the pitch or the frequency. And so here you've got a big heavy oxygen molecule and a tiny light hydrogen molecule on it. That's going to be able to vibrate really quickly. Whereas if I've got an oxygen that is hooked up to something else, like a big chunk of the rest of a molecule, that's going to wag really slowly. Right? So you got a big heavy thing at the end of your bond. And so your bonds are going to act like springs that are holding your molecule together, and they're able to vibrate or oscillate or rotate. And that's going to depend on how heavy the things are. Right? So got a nice light hydrogen over here. Right? So that's going to vibrate fast. Right? And here we've got an oxygen hooked up to an R, where the R is some aliphatic thing, like maybe a CH3. Right? That CH3 is going to be way heavier than hydrogen. It's going to vibrate slow. If you look at the bond strength, so if I look at a, where is it? I need a carbon-carbon. All right, so here's a carbon-carbon double bond, and here's a carbon-carbon triple bond. Right? The stiffer and shorter bond, so a triple bond, is going to have a higher frequency. Right? So I've got a stronger spring. That stronger spring is going to vibrate faster. Did you guys like ever get on like those little kiddie rides in the park where it's like a big spring on the top, there's like a pony or something, and you're like boinging back and forth like this, right? And if you get like a grown up on there, it's like, ooh, ooh, really slow. But if you put like a toddler on there and you just hit the back of that thing, that's right. And the little kid's like, yeah, it was fantastically fun, right? Well, if you change the mass on top, it's going to change the frequency. And if you change how strong that spring is, it's going to change the frequency too. So you get like a nice stiff, strong spring, it's going to vibrate fast. If you've got something that's a kind of lazy spring that's stretched out and old, it's going to like it goes back and forth, right? So that's not going to be nearly as fast. So how do we deal with noise is an important question. Right? So we talked about some of the sources of noise or interference. So what is noise, right? So noise is really just signal we don't want to see, right? So noise could be a fluctuation that's coming from somewhere else. It could be an interference. So I'm in a crowded room and I'm trying to talk to somebody and I've got a lot of acoustical noise from other conversations. Those other conversations are going to be signaled to somebody in that conversation, but to us, because they're not part of that conversation we want to be in, it's unwanted, it's noise. And we've got different sources for noise and different ways to deal with noise. And so probably the most important way we can deal with noise is what's called signal averaging. You can get some really dramatic improvements in noise by doing signal averaging. And what you're doing is you're taking one scan and then you're going to add it to the next and add it to the next and add it to the next and then divide. So you're basically adding up all of your signals and then you're going to divide it to bring it back down to the same level as that before. So you've got some sort of noisy signal, right? You got all these like high frequency components on there. You got a peak here, maybe another peak here. You can figure out the noise is maybe 9 units, and you've got some signal in here that's 14 units. So our signal to noise ratio, or S to N ratio, is going to be 14 to 9. Right? So if we look at our signal to noise ratio, we can improve that by running multiple scans. All right, so if you think about your noise, right? So your noise is going to be random and your signal is always going to be there, right? So when you add up multiples of this type of signal down here at the bottom, that noise is going to fluctuate on either side. So you will have some cancellation of the noise where it was positive one time and then the next time it's going to be negative and the next time it'll be positive, and maybe you get 2 positives in a row and then like 3 negatives, but that noise is going to start to cancel itself out. Because the signal is always there, that signal is going to reinforce itself each time, right? And so your signal will be steady, your noise will be random, and when you add up that noise over time, it's going to zero itself out. So if you're going from 1 scan to 4 scans to 16 scans to 64 to 256, your signal is still staying there, but your noise is canceling itself out. Okay. Another way of dealing with noise, if you've got a digitized signal, is what's called the root mean squared, or RMS noise. Does this look familiar? Yeah, that's basically the same sort of thing that we saw with our standard deviation. And so we're looking at, here's the difference between some value and an average value, and we're squaring it and dividing it by n, right? So by this method, the noise at the bottom has a signal to noise ratio is 14 divided by 1.8, or 7.8. Because the RMS noise is 5 times less than the peak-to-peak noise, it's important to specify which measure is being used. Usually, you're going to see this guy showing up most places. It is more common because it's giving you a little bit better signal to noise ratio, right? If you got a choice between an S to N of 1.6 and an S to N of 7.8, you go with the 7.8. But it's doing that same trick that we saw with our standard deviations, where we're taking something and we're squaring it, that's the square part, and we're taking the square root, right? And then we're dividing by n. So this is the mean part. All right, so we're dividing by n, that's our mean. And this part here is our square root. And the fact that we're squaring our things to get rid of plus or minuses, that's a terrible plus. To get rid of our plus or minuses, that's why it's called the root mean squared method. Right. And if we're going to take repeats of our spectra, our signal is going to increase by a factor of n. So the more we take our spectra, so if we take 4 spectra, our signal increases by 4. If we take 4 spectra, our noise is going to increase by a factor of the square root of n. So n goes up faster than the square root of n. So every time you do a set of 1, 4, 16, 64, 256, you're improving your signal by the square root of n. So our signal to noise ratio improves by a factor of square root of n when n spectra are measured. So that's why you're going to see things that are going to be in common breaks, like 4 or 16, right? So the square root of 4 is 2. So if you take 4 spectra, you have doubled your signal to noise ratio. And that's because our noise is random. Right? It's going to be positive one time, negative the other time. I add them up, they're going to cancel each other out. So your noise is going to be canceling itself out. Your signal is going to keep adding. Will you always get better? There's some limits. Will additional averaging always improve your S to N ratio? Not always. There's usually an upper limit at which point you're not going to get anything better. Part of it is that you need to keep going. Like if I want to go from, right, like 1 to 4 isn't that big of an ask, but going from 4 to 16, you're like, okay, now I got to wait. Like if each of these takes 1 second, right, this is a 1 second acquisition. This is a 4 second, this is 16. And now to improve this, you're going up to 256. And are you going to really get better than 250? Like the difference between 256 and 64, you may not care about. Right? There's usually an upper limit on the number of averages that improve the signal to noise ratio. So this plot over here is going to show the standard uncertainty versus the signal averaging time. So averaging up to 200 measurements results in an improved uncertainty, and above 200, the uncertainties increase due to drift in your instrument. And so you might actually, because you're taking 256 of these measurements, right, your light bulb might be changing in its intensity, or your instrument might be moving it because maybe you're moving things around. So you might have some instrumental drift that happens. So you might have another source of noise. There are actually lots and lots and lots of ways to deal with noise. We could go on for like a good week about just how do you deal with noise, because noise is one of those things that is always with us. It's like, how do you deal with it? You can get noise from a couple of different places. White noise. So if you guys are familiar with the term white noise, it's what we call Gaussian noise. It's random noise that's always present due to random movement of charge carriers in an electric circuit. So Johnson noise, arrival of photons or charge carriers of the detector, so shot noise. So if you turn on an old school TV and you see like, and it's the static, that's your white noise. It is over all frequencies equally. You can have 1 over F noise, so a slow change in the response of an instrument due to various causes, such as slow changes in the instrument components with temperature. 1 over F noise is kind of always with us. Variation in your power line, so how the power changes or the amplitude changes as a function of frequency. You just have lots of more random stuff that are moving slowly, and then you have stuff that are moving fast. Right? You want to think of it that way. You can have line noise, so interference noise, so noise concentrated at particular frequencies. So if you were in a conversation, right, you would look at, well, somebody else is talking at the same pitch as me, I'm going to end up with interference in that region of your frequency. So here you've got something like 60 hertz from a power line. right? So you'd see something at 60 hertz, 120 hertz, multiples of 60. These guys are pretty easy to deal with in some ways because you know they're there. And you're just like, nah, if I see a spike at 60 hertz, I know where that's coming from. It's coming from my wall. 1 over F noise. One of the things we can do is we can actually move our signal out into this quieter region. And then signal averaging is what gets rid of our Gaussian noise. So in our double beam spectrometer, we've got noise attributed to the sources that are independent of the light level, and 2 sources that are proportional to the photogenerated current, and 3, the intensity variation of the light source. So when we do our beam chopping, right? So we just said it's going to move that in 2 different directions. It's actually going to do a little bit more than that. So when we have our beam chopper is spinning at a particular frequency. What that does is going to move our analytical signal from 0 frequency to the frequency of the chopper, so the frequency at which we are chopping up that beam. The chopping frequency can be selected so that 1 over F noise and line noise are minimal. So what you are doing, so you got your mirror, right, and your beam chopper, and it's sending it in 2 different ways. And now you have, so if you look at the signal from your chopper, right, you've got some stuff where it's on, right? And then it's going to be off and on and off and on. And this guy's coming in at a particular frequency, right? This guy's got a frequency with it. And if I'm doing that 10 times per second, I'll call that 10 hertz. What I'm doing is I'm taking my signal from my spectrometer and I am adding it to, or what's called convoluting. I'm convoluting the frequency of the chopper plus my signal. And so what I'm doing is rather than looking at here, where's my signal, right? This is my signal happening here at 0. I'm actually going to move that. And so if I got some signal in here, it's buried in all this noise. I'm going to move that guy out over to here where now it's at the frequency of the chopper. And so I've moved it from my regular frequency happening at 0 out over into this less noisy region. And I can plan it so that it's not going to hit one of these guys too. Right? I can then deconvolute my signal and then bring it back down into the same region as I saw before. So that's going to move your signal from one space to another. You can just smooth your data, right? So you can, rather than looking at your data and averaging it up in terms of like, I'm going to take one, and then I'm going to go to another time, and I'm going to take another one, I'm going to take another one at another time later, and adding them up. You can smooth horizontally, so smooth across frequency, and do averaging that way. So I'm going to take adjacent, so here's my original data point, right, my original signal, and if I do what's called a moving average, I'm going to take 7 data points at a time, add them up, and I'll make a number. And then I'll take mine, move it over again, and I'm going to take 7 data points, I'm going to average those, and we'll get another number. And what that does is it's going to smooth out your signal. So a 31-point average is probably going to be way too much, by the way. Hopefully way too much. This guy's okay. A 7-point average should be okay. All right. That's just going to be basically like a rolling average as you're going from left to right through this. The Savitsky-Golay method is a little bit different. We'll do that in, I think we got the slide for that. All right, so yeah, so 7-point moving average. So we got solid circles. These guys are representing your original data points. The 7-point centered moving average, you're going to replace data point 4 with your open square, whose intensity is the average of the 4-point intensity and intensities of the 3 points on either side. So to smooth point number 5, move over to this next guy, you're going to look at the next guys over, and you're going to take all of those 7 points, and you're going to divide them by 7, and then you're going to put a new square in here, which will be probably about there. Right? And so you're accounting for the data on the left-hand side and the data on the right-hand side because it's noisy, and that noise kind of cancels itself out. Sometimes it's going deviate a little low. You're averaging across the data points rather than through time. You do that and you end up taking a small hit in some of your resolution. And so sometimes you will miss small peaks. So downside here is, number one, you might miss something small. You might miss a small peak. And two is you're going to end up shifting your peaks. And three, it's not good if you have a high frequency, if your signal is high frequency. So it's going to kind of blur those out. It's like putting on a pair of like dirty glasses, right? You're going to lose some resolution, but it's going to give you a smoother picture. Like if you do the Gaussian blur or like image smooth on Photoshop, it's the same thing, but in one dimension. Savitsky-Golay smoothing is going to do with, rather than an average like that, it's got the advantage that you're going to retain those sharper features. So if you've got some high frequency stuff in your data, like if you're looking at your IR spectra, right? Your IR spectra have these really sharp peaks going on in here, right? And if you did that as an average, a moving average, well, these guys here might get blurred out. So your Savitsky-Golay smoothing is going to retain some of those sharps. It's going to do a cubic fit to the least squares points instead. So basically you're looking at, well, here are my data points, and I'm going to do a cubic fit to them instead of just averaging them. How do you do this practically? You just have the machine do it. And you click a button that says smooth data, and it gives you an option. Just know that rather than doing just a straight average, you're fitting this parabola instead. And there's other methods that you can do. Actually, usually it's an upside down parabola, but there are other methods too that are like, how do you basically do this kind of balance between, I want to get rid of my noise through some sort of averaging, but I also want to retain. So this guy's doing a parabolic fit or a cubic fit. You can do ones that have like a third order polynomial, or ones that have like a little triangle instead. So there's all kinds of different ways to do it. Cool. So now we're into emission spectroscopy. So you guys have all seen something like this at some point. If not, we will just remind me, and I can get out a Bunsen burner and we can do some cool stuff where we burn some lithium or some sodium or some potassium. And you get different colors, right? Because you get different colors of emission. So we have looked at that already, but fluorescence is also an emission technique where we're looking at the photons that are coming off. Here we are throwing in photons of a particular wavelength, and we're looking at what we call Stokes shifted. S-T-O-K-E-S. Stokes shifted. Stokes shifted. So that's going to be a change in wavelength. All right, so you're going to end up with a shift in wavelength. So you're basically taking energy from one wavelength, and you're seeing energy that's coming back out at another wavelength. And usually it's a downshift. That's a Stokes shift downward. Sometimes it's a Stokes shift upwards. But the process for that is similar to molecular absorption. So you have to undergo a molecular absorption process from a ground state to some sort of excited state, and then maybe to one of several vibrational states. We got some vibrational levels here. And that's these guys. And then, so we end up with some absorbing a photon, right? So now my molecule's got a little bit more energy. I can vibrationally relax down to a lower vibrational state. or I can undergo an internal conversion from one electronic state to another electronic state. When I release that photon after it's undergone vibrational relaxation or internal conversion, I'm going from a ground state, ground electronic vibrational state, down to a lower electronic state and to one of several possible vibrational states. And so you end up with an excitation and an emission spectrum. So if I looked at my absorbance profile, right, I am absorbing photons from ground up into here, and I've got 1, 2, 3, 4, 5 levels, or from here up into this guy, and I got 1, 2, 3, 4 levels. Right? And so I end up with 1, 2, 3, 4 peaks in my excitation spectrum. So this is really an absorbance, right? And then if I look at the photons that come out, my photons that come out are going from here down to my ground state, but a couple of different vibrational levels. And so I've got my emission spectrum, my photons that are coming out, where I've got a couple of different vibrational levels that they're going to. So to be vibrational level is let's see, V4. 4 and V3 and V2 and V1, right? So I end up with what looks like a mirror image of those two things. One is going to be my absorption and one's going to be my emission. Right? So the emission is photons that are coming out. These are going to be in all directions. Right? Those photons that are coming out at me in all directions. Here's an example of a, this is fluorescein. This is a pretty common fluorescent dye. It's got a really high what we call quantum yield. So if I throw in one photon that's up here in this region, I'm probably going to get close to another photon out. You can still see that it's got that same mirror image thing going on. It is, you will see this, and like if you see anything that's like that kind of yellowish greenish color, like this very, very characteristic. I've got a clipboard in that color. It's going to fluoresce yellowish green. That's coming from fluorescein. That's this molecule here. A lot of these fluorescent molecules are going to have these kind of anthracene looking systems where you got conjugated aromatics going on in here, where they're able to absorb stuff. If you wanted to do fluorescence like this, right, you can quantitate it. So this is Beer's law like. Right, it's Beer's law like, where the concentration of fluorophores that are in there, you can track that and get more fluorescence out. So if I throw in 10 photons and I want to look at the number of photons that are coming back out, as I increase the concentration, the number of fluorophores in there, I'm going to get more signal back out. You do have a roll off on the top, and that's coming from a process called internal filtering. Internal filtering, right? So you've got this fluorescent molecule here, right? So it's absorbed a photon, and now it's giving out photons in all different directions, right? Well, one of those directions, it could go over here, and this photon that it gave out now interacts with another fluorophore who sends that photon back out this way. And so if you've got a lot of things in your solution, right, the chances of this guy's fluorescence photon making it back out to the detector over here, oh, that's terrible, it's supposed to be an eyeball. Get some lashes. Right, so the chances of this guy hitting an eyeball, right, decrease if I got stuff in the way that is going to send that photon out in some other direction. Right? Your instrumental setup is very similar to either a single beam or a double beam instrument. The big difference here is that this optical axis is at 90 degrees, right? We're not looking at this, right? So this is the direction we do our absorbance, but because our fluorescence happens in all directions, we want to minimize the photons that are coming from our light source and only look at the ones that are coming from our sample. So we're going to set this detector out at, 90 degrees. Right, so here we're going to throw in a bunch of stuff, right? We got some sort of filter, right? We're going to look at the photons that are coming out. They're going to go in all directions. We want to look at the ones that are coming out back here. There are reasons why you don't want to do this at, right? And then we're going to say no, right? We're not going to do this at like 45 degrees. You could, in theory, do it at 45 degrees. It has to do with like what the scattering profile is for how those things actually emit those photons. Now, you definitely do not want to do it directly in line because you're just going to end up blinding your detector. Right? Here, right, because you've got a very sensitive detector where it's looking at 90 degrees, you are looking at signal on top of no background. So it's like looking at the stars at night, where you're still seeing the energy from the stars during the day. It's just that you've got the sun in the way, right? And so if you can remove the sun, right, remove all the photons that are coming this way and only look at the photons that are coming from your sample, you've got a low background and you see the appearance of signal on no background. So it's a different configuration experimentally, but that also means that you can have more sensitivity. And you've got greater sensitivity with that. Right, so your fluorescence methods are really good at quantitating small concentrations of things. And you don't want to go to high concentrations, right? So if you're dealing with a high concentration of fluorophores, right, you get this internal filtering that happens. And you can actually see a little bit of that internal filtering at high concentrations, where this guy's kind of like this yellowish, almost orangish that's happening, as opposed to the greenish. So it's, once you see that internal filtering happening, it's kind of weird, and you're like, ooh, that's what's happening. If you're doing with a high-end instrument, you're going to have two monochrometers, right? So one is going to do your excitation, and the other one is going to do your emission. Right? So this is actually an emission. That's your emission monochrometer. And so this is going to give you your excitation spectrum. So this is really just absorbance. And this guy over here is going to be your emission. You can do this quantitatively. Right? So you're going to do just like you would before. You're going to do a standard curve. You can go from parts per thousand all the way down to single molecule. So doing single molecule fluorescence detection is pretty routine these days. Lots of people have done it back when I was a young dad. in the ancient days, when dinosaurs still ran loose on the earth, fluorescence detection was right on the edge of doing single molecule. They had not done single molecule yet, but they were close. Right. So yeah, you can quantitate. Yeah, like I said, your fluorescence is going to come in all different directions. Those are just some of your useful equations, but I think I'm going to stop it for right here. All right, if you guys have any other questions, let me know.
I have a couple of questions about the lab, the HPLC lab. So I could not find name labels on those. Are they chronological? Like the one on the top went first and then the one on the bottom went second?
No, they're going to be alphabetical. So it should have name or at least initial labels in there.
Okay, I'll go look for those. And if I
can
find them,
double check. You know, I think I got everybody's initials right in there. So just double check, because like one will be like AJ1, AJ2, AJ3, and then the next one might be OL1, OL2, OL3, OL4. So it should say like kind of in the upper left, I think, like what the sample name was.
On the HPLC?
Oh, shoot. Sorry, I'm thinking the GCMS because I've been the one doing that. For the HPLC, I do not know. Email Avery or Grace and see if they've got an answer for you, because I don't know how they did that and how they set that up.
All right.
My guess is, did you write it down in your lab notebook?
Oh, yeah. Yeah, I did. I didn't even think about that. I can probably just compare the two.
That lab notebook, it's useful for shit. Yeah. Yeah, so if you got it in your lab notebook, then just use the value you've got in your lab notebook. And Kim said that the HPLC are unlabeled in chronological order from what I could tell during the lab, but emailing the TA is the safest bet. And then some have the whole name.
So for the HPLC, I think one of the things on the rubric was like the actual sketch of it, but then like we never really got the sketch.
Yeah, so you do not have the actual chromatogram, which is okay. So just make a note in there that says you do not have the actual chromatogram for your HPLC. Also for the HPLC and for the GCMS as well. Like if you use the spreadsheet that I gave you, it may give you a standard deviation or it may not, because you've only got one data point. All right, so you've only measured your unknown one time. That should not be a problem with the GCMS lab, but with the HPLC lab, where you've only got one data point and you're doing a regular old standard curve, it might just say, I can't give you an answer on this because you've only got one, you only measured your unknown one time. If that happens, you cannot then do, well, either way, you can't do a confidence interval because you've only got one measurement. So all you want to do is report your standard deviation. Don't worry about doing a confidence interval. If we ran it 3 times and we have the time to run it 3 times, cool. So all you're going to do is you're going to say, this is the standard deviation if you can get one. If you can't get one, then you just report the value you've got. And then you say, I cannot do a confidence interval because we only ran our unknown one time. Okay? So nobody should have a confidence. I mean, it would be great if we had time to do it and run everybody's thing 3 times, but we don't.
I thought that I heard you say that like we could do plus or minus like.
Yeah, so you can do plus or minus whatever your standard deviation is, basically. And so if you need to report a confidence interval, how you would do that is say plus or minus the standard deviation. If you cannot get a standard deviation, then you make your number 2 significant figures and you say plus or minus 1 in whatever that last decimal place is. So if you get 0.04237, you report it as 0.042 plus or minus 0.001. So if you had, here, I'll write out 0.0423, so for example, you got that, right? Then you're going to make that into 0.042, and then you'll say 0.042 plus or minus 0.001, like that.
So that's if we don't have a standard deviation?
Yeah, if got no standard deviation. Otherwise, it would be 0.042, 0.04237, and then maybe you'd get a standard deviation of, the machine would report out that maybe your standard deviation is 0.003, right? So then you'd go 0.03, and you then truncate this guy. So this guy's got 2 decimal places. This guy's got 2 decimal places. So you do 0.04 plus or minus 0.03. And I just kind of made up numbers. So, maybe this guy's 0.003 or something. I don't know. All right, and that makes sense as to what to do. So this is if you've got no standard deviation. If you have standard deviation. All right, other stuff?
I also have a question about the lab grades. I've only gotten up through the KHP titration. Do you know about when some of the other ones will be rolling in?
That's weird. Yeah, just email me and have me take a look at it, because I'd have to go like into the grade book and see what's going on. I know that some of them, excuse me, some of them may not have been released yet, where it's like, because if you release it and it's not got a grade in for people, then it shows that they've got a 0 because grades are released, and then people freak out because it's like, oh no, why do I have a 0 for this thing? And it's like, no, because you haven't done the lab yet. So I will check on whether or not things are released yet. So because that's usually a pretty easy one to fix.
Okay. All right. Thank you.
But yeah, so if you see a bunch of zeros in there and you've turned stuff in, or it just hasn't been graded yet, I will let you guys know. But I'll check in on this. Check 219 grade release. All right.
One more question. So with the lab notebooks, do you want us to like for mine, like I like made my charts and stuff like in Excel and do I have to turn them off?
Put them in there.
Okay, so I have to do that. Can I just use a sketch or no?
You can do, like, if you don't want to print stuff out, because I realize that that might be difficult for people, you can just like kind of draw a sketch and then reference the lab report that you turned in or something, like what the file name is for the whatever the document is that you've got it on. So you know, see, you know, lab 7 report.
Yeah, because like
or something. But yeah, definitely include at least a sketch of what those things look like. And if you know, you could write down what the equation of the line is if you've got that, so that you know, if you pick up your lab notebook again in the future, you're not just like, what the hell did I do here? So
would it be possible, could I like because I had it in like a PDF file, could I just like make like new pages so I don't have to like print it off and stuff and then just like add it into it?
Yeah, that's fine.
Okay, thank you.
Yeah, no worries. That's a good idea. Because you know, if you are doing, because you're doing your lab report as a digital document, you know, if you wanted to just like insert at the end of that, like if you wanted to merge that as a PDF at the end and then have like that printout, then that's fine too. Or you know, if you're taking it and you're scanning it with your phone, you know, just like literally take a picture as one of those pages from your lab report of the computer screen and just say, this is the file that's coming in there. Okay. Other questions? All good stuff. But we're done with spectroscopy, by the way. Yay.
So
it kind of makes me sad, but.
Sorry. I have a few questions just about like my SSA graph for the GCMS. Do you want me to just like leave and then go on to your office hours? Or just...
It depends. Do other people have questions about the SSA curve? Okay, since nobody does, give me a couple of minutes to shut this down and upload it and stuff, but I'll meet you in office hours in like 10, 15 minutes if that's okay.
Sounds good. Thank you.
Alrighty. All right, nobody else has anything. I'm gonna stop this, upload it, and then head on over to office hours.